1 year ago, I was at this conference. I gave the keynote, which is this title. How many of you were in Florence 1 year ago for? Okay, so a good half of the room. So it was somehow the prequel to this talk. In that talk, I wanted to describe why, in my opinion, we have fundamental problems in Python about performance and what are the blockers and why Python performance is not as good as it could and should be. There is the link to the talk for the extended version, but the very short version is that Python is very hard to optimize if you are an interpreter or a compiler because everything is dynamic, everything can change at any point in time. Like you can add and remove modules at runtime. You don't know which modules you are going to import until the very last moment. You can monkey patch classes. You can change the dunder class of an object. And for a compiler, it's very, very hard to make sure to implement full semantics and have good performance. There are projects like PyPy. I've been doing PyPy for many, many years. It's probably the best example in this area. It managed to reach very good performance, but with shortcomings because you need a very complex implementation of a JIT compiler. And most importantly, you need to be very, very, to know the internals of the compiler very well in order to get the maximum performance. And it happens very often that you arrive at in a good state with your speed, and then you change a line of code somewhere, and somewhere else everything becomes 10 times slower because the JIT compiler can no longer make assumptions, or the assumptions that it makes are wrong, and that's what I call like performance cliffs. And so it's very hard to reach consistent speed. But at the same time, I mean, that's why Python is a nice language. So if you want a language which is not dynamic, we can just use Java and be happy with that. How many of you would like to do that solution? One, okay. So this was like 1 year ago. Like the talk of today is, I like to think of Spy as kind of a thought experiment. How much dynamicity you can remove from a language so that it's easier to make it fast, but at the same time, it's still Pythonic, and we don't end up like Java. I mean, nothing against Java people, really, but it's just an example. So let's see how far we can go. This is also a slide which was in the same talk as 1 year ago. It's just random code, which I don't even know what it does. But like as humans, we know very, very well what it does. Like we can read it, and we are obviously importing NumPy, and we obviously have a constant which is 10, and we have a function which takes an array and a scalar and returns a float because we have type annotations. But the compiler cannot assume any of that because I could have an import hook which imports something completely different, which is not NumPy. The constant n could be changed by someone else in the program. Type annotation could just lie because Python type checkers are just not, I mean, they cannot. It's like provable, impossible to make them completely safe. And so as a compiler, you cannot rely on this assumption. But as a human, we do, because nobody will write code which does all the strange things I was saying. So like the idea is to make a language in which what the humans see is what the compiler can, human and compiler kind of agree on what are the rules. I claim that in practice, we already use a subset of Python, because there are a lot of stuff which are super dynamic and part of the language which you shouldn't use. There are cases, like you can really, I've written code which modify the dunder class of an object at runtime. And yes, but most of the time you shouldn't. And you shouldn't monkey patch classes unless in very specific situation. And the modern tendency in Python world is that people seem to really like static typing and type checkers because it improves safety. I mean, perceived safety, I would say. And it makes life in IDE easier, but it doesn't help performance at all. So like Spy start from here, and let's try to design a new language. I mean, it's a Python variant. It's not something completely different, of course, but some of the ground rules are different enough that you can consider it a new language, but with rules designed to match this kind of behavior which you actually see. The other problem which I want to tackle is that in Python you have this, like, the two language problem. Like, you have a high-level, nice programming language, which is Python, which is like nice to use, but it's low. And when you want performance, you need to go lower level and change language. You need to write stuff in C, C++. Nowadays, everybody writes stuff in Rust, or use tools like Cython, and makes very, very hard to like, you need to know two languages, you need to manage complexity, you need to have like a building tool chain, like it adds a lot of friction. And that's something that also Spy wants to solve. So the goals of my project is that I want something a language which is easy to understand and Pythonic. Like, a lot of the patterns which we like in Python are still doable in Spy, but at the same time, it should be easy to implement. You shouldn't need a PhD to implement a fast Spy compiler. You shouldn't use like state-of-the-art JIT compilation technique, anything like that. Like, right now, I'm working on it alone, and even alone, I can go pretty far. Performance should be predictable, like no longer try to optimize and finger crossing. Like, you should be able to predict and know what is slow and what is fast. And you have one language, and with the same language, you can operate at a low level if you really need a super fast, super high performance. But you can also, like, from this, like low-level core, you can build abstractions which are zero cost or very low cost, so to build a nicer libraries and user experience. An explicit non-goal by design is to be 100% compatible with CPython, because I claim it's not possible to achieve these goals and keep backward compatibility. We tried. I've tried for 20 years, and I don't say that we failed, of course, but I really think that it's not possible. I'm perfectly aware that I'm not the only one in this space. There are a lot of variant / restricted subset of Python / JIT compilers. Everybody has a @JIT decorator nowadays. So yeah, I'm just adding a new one. So from this point of view, I'm not making the situation easier. But from another point of view, I think that Spy actually can help to unify. It's a very ambitious goal. Maybe I will not reach it. But like a lot of these like restricted languages, everybody implements a slightly different restricted version of Python, and which different rules and type systems which are not really compatible with each other. And if you cannot really develop in an interpreter way, because you need to compile them instead to see what is the actual semantics. And Spy can be used as a common front end for all of this. So like Spy takes care of it is a high-level language, lower it to a restricted core, which is statically typed, and specialized compiler can go from there and well, do their magic. So that's something that, for example, at Anaconda, we aim to do with Numba. So I'm in the same team as them, and the idea is to use Numba as Spy as a front end for Numba, so that you will be able to reuse libraries written in Spy automatically with Numba, and, for example, use the GPU capability of it and things like that. But nothing like, ideally, other specialized compiler can do the same and get a lot of Spy features for free. So before going on, I think it's important to underline what is current status, because the basic idea of Spy works. You can use Spy as a standalone compiler to generate executable, which can be distributed multi-platform. You can compile to native or WebAssembly or mscripten in the browser, but only if you use only SPY libraries, let's say. You can build a CPython extension, so you can integrate with the broader Python ecosystem. Right now, it's only in one direction. You can call SPY from Python, but not Python from SPY. Of course, it will be possible, but later. And I have like this kind of low-level core. I can write like a simple struct. And I have a super simple, incomplete, half-broken implementation of array, which is not really for like general usage, but it's enough to do interesting stuff, as we will see very, very shortly. What doesn't work is that like everything else. Like SPY at the moment doesn't have list and dicts, just to understand where we are. But it's on purpose. Like the idea is that list and dicts will be able, like I will implement them in SPY itself, or maybe you, like contributions are welcome. So right now, like, you cannot really use SPY for anything real, but you can use it for something. So this is an interesting demo for those who were yesterday at Fabio's talk about PyScript. So I encourage you to try it, because it's a PyScript application which runs fully in the browser, which also has a kernel of computation written in SPY for speed. And you can just read it on your phone, and I can run it on my computer, and we see what it does. So this is the demo. It does some image processing. By default, it starts by doing computation in Python, pure Python using NumPy. This is the fastest thing which I was able to do with NumPy, so without resorting to any compiled Python. And you see it's very, very slow. It goes to 0 FPS. And we can, by clicking here, we can switch to SPY. It takes a while just to take the event, the click event, because the slow computation is blocking. And then this is the speed with SPY, like 60 FPS, so I don't know, yeah. And while we are at it, I would like to try to do the most complicated selfie ever. So, please, someone take a picture. So, I survived. So this is like introduction. That's like where we are going and what you can do. The second part of the talk is really like a deep dive into the internals. I'm going very technical and very explaining how a lot of the rules and the language works. So the idea is to give you a rough understanding and intuition of how things how I can reach the goal that I was stating before. So the general architecture of the project is that I have an interpreter, which is a super simple AST-based interpreter. Right now, it's written in Python, so it's super slow because to run a SPY program with a SPY interpreter, well, you have double interpretation. So it's awfully slow, but for now, I don't care. Eventually, SPY will be able to compile itself, so the interpreter will be compiled to C and to native code, so it will be fast. Then we have some magic, which I'll explain later. And then I also have a compiler. So the same program you can interpret for development's sake and have all the nice features that interpreter gives to you when developing. You can compile, and the general architecture of the compiler is that I take the AST, I generate C code, and then I use a normal C compiler for generating native code. Why this choice? Just because it's very simple. It's the easiest way to generate lower level code. I could totally use different backends. I can imagine having a LLVM backend and then use LLVM toolchain for the specialized optimization if I want. But at this point in time, that's not the kind of speed. Once the language is done and functional, I can imagine doing more optimization at very low level, but right now, if we reach the speed of C, I think that we can be happy enough. And generating C code also gives you a lot of interesting opportunities because it makes it very easier to integrate with existing tool chains and tools. So, for example, this is something which I didn't think at the beginning, but I discovered that, okay, since I'm generating C code, it's very, very easy to bind it using CFFI, and then you can get your spy code inside CPython through CFFI. So that's how that's how this demo works, for example. And that's like, it's C compiled to WASM and bind it to PyDide using CFI. So it's kind of super cool that it just works out of the box without too much. So, and before going, it's also important that I have both interpreter and compiler, because all the other projects that I mentioned before, one moment. All the other projects which I mentioned before, they suffer of a common problem, which is that you have Python code which run on interpreter, on the Python, on CPython interpreter, but then the semantics is different. And I want to avoid this distinction. The idea is that once you have run and tested and developed your program using the SPY interpreter, compilation is just transparent, and semantics should not change at all. I'm running tests, like I have a lot of tests, and thanks to Fabio who showed me how to write a lot of tests. I really take inspiration from him. And each test is run in 3 different modalities, and to check that the semantics is completely the same, including error messages and stuff. So this is the hello world. In SPY, we have exception to the rule, but generally speaking, type annotations are required as in the signature of functions. And then I have a, right now super limited, but eventually can become better, form of type inference inside function bodies. But so at the boundary between functions, you need to annotate your types. And so this is a hello world, something super simple, a print, and I call a function. And let's see. So I can, as I said, I can run it. This is the interpreter, but I can also compile. And this generates a file, which is an elf. And I can, of course, execute it. Nothing special. But, like, for example, I can compile for different targets. So what if I want them scripted? Then this generates a JavaScript file plus a WebAssembly file, so I can run it inside Node or inside the browser. Or I can build for WASI, and then to generate a WASM file, which I can run with WASM time. Or I could also generate the CFFI bindings. In the slides, I also included like the output of what I'm showing, but I think it's nicer and more entertaining to see me typing, and instead of just seeing a lot of. But I include them for like posterity, let's say. So, so we said we have this general architecture in which like you have the interpreter, AST based, you have some magic, and then you have the compiler. What is the magic? So a lot of the logic happens in what I call Redshift, which is a form of partial evaluation. So the general idea is, in Python, Python is slow because at every point in time it needs to recompute a lot of logic which is always the same. Imagine if you are having an operation or calling a method, it needs to do the lookup of the method again and again, checking the class, checking whether something has changed, and this is slow. But a lot of logic in practice doesn't change, so the idea is to have logic same or similar to Python, but in such a way that we can pre-compute as much as possible in advance, so that what remains is something smaller and faster. I use like a color mechanism just for have some vocabulary to talk about it. And the idea is that the blue code is what can be optimized away safely, And the red code is what remains, and it's actually executed at runtime. That's why this step is called redshift, because it takes something which is blue and red and moves, as in astronomy, everything to the red and then removes the blue. Since we are in Bologna, this is not related to football, especially because I'm from Genova and red and blue are the wrong colors of the city. So I want to make sure. Actually, in PyPy, we use same terminology, but it's green and red, but someone pointed out that green and red is not colorblind friendly, so yeah, I decided to switch. The other difference with the slide that we saw before is that, yes, this AST which we feed into the compiler is lowered. So it basically is the same like with lower level operation, which are easier to translate to C. And let's see still our hello world example, which I can show it again. So we have like function to add two numbers and two prints. So I can redshift and we can see this is the result. This is just a pretty print. What is internally is to manipulate the AST, but then I have a pretty printer so that for the end user it's very easy to understand what's going on. And there are a couple of interesting stuff. So for example, the print is specialized by type. And this is something that you can do statically, because since we know the types, then we know that this print statement is always executed with same type, and so we can kind of specialize the version without paying the cost of dispatch at runtime. We also see that everything gets what I call a fully qualified name, and I represent with backticks here. So it's not when I call something, I don't call a generic print function and I need to do lookup. And where is the print function? Could be in the local scope, could be in an outer scope, in a closure, could be in a global, could be a built-ins. Like, this logic exists in Spy. It's just that during Redshift, I do it like in advance, and then I put the result as a fully qualified name so that I don't have to redo the computation again. And you can see that even when I define a function, I define it with a fully qualified name, which exists uniquely in the virtual machine. And the plus, well, this has become like a very low-level specialized function call, which then the C compiler knows to map back to a plus operator in C, but then it's really like a machine operation. It's no longer like this super complex logic that we have in Python. And same for type annotation. Type annotation are evaluated at blue time, so what was int has been pre-evaluated to like built-ins I32. What is blue? Like, the idea is that the more blue stuff we have, the better it is, because we have less stuff to do at runtime. Not a lot to start with. So like literals are blue. Constants are blue. Constant, like I have a constant and I store it in some global variable, and then I promise that I don't modify. It's also considered like a blue data. If I have poor functions which don't have any side effect and don't depend on global state, and they just depend on the parameters or on some other blue global state, well, these are also considered blue. But the escape hatch is that I can also mark functions with this decorator as blue, and then I'm basically promising that it's safe to pre-compute them away. And actually, the rules of the language are designed so that like, you really cannot do anything non-blue inside a blue function. This is an example. I have this function written by ChatGPT. I don't know if it's mathematically correct. I don't care. It's not important. I care if I need to compute a circle. But so this is a function which computes the value of pi, and I have a function to calculate the circumference, and then I have like some code. And what we can do is we can run it. What's the name again? Okay. I hope it's this one. Yes. It works. But if I do Redshift, that's when things become so interesting, because we can see that the prints has been specialized, but most importantly here, I no longer have like the call to Py, and also here. And the blue function is completely gone, because I don't need it after the shifting. We will see now how it actually works. So the idea is that like I take the AST, I color all the nodes, and then whatever is blue, I do the computation, and I generate a new AST. And it's easier to just see in graphics what happens. So this is the code. So 2 times call of P, pi times R. So this is AST. It's a bit small, but I hope it's visible enough. So it's like the standard textbook compiler class in any computer science program. So I have a binop, which is times, and I have 2 operands. This is another multiplication. This is a variable. It's reference to the variable R. And then here I call function pi. And then I start from the bottom, from the leaves of the tree. And I see, for example, that this is a liter, so it's blue. This, it was like name of pi. And then I do name resolution as something which, by design, I can do at blue time. So I walk over all the scopes, and I see that pi is actually a global a function in the global scope, so I can substitute with this fully qualified name constant, which reference module pi. This is like how I spell fully qualified name. And also R, I do resolution, and then I know it's a local variable now. And it's like this is red, because local variables are always red, unless I make them blue explicitly. And then I walk up. So this node is calling a blue function, so it's blue as well. And now I can pre-compute it, and then that's the magic. Like the compiler calls the interpreter to do part of the computation. So here, during Redshifting, I go back to the interpreter and I tell it, okay, please evaluate this and tell me what the result. The result is 314. And then now it's again blue, and I can walk up. And this multiplication is also blue. So I call the interpreter again, and I get the result. And then I walk up, and then I have the last multiplication, which is with 1 blue and 1 red, so it's red. And then the whole expression is basically red, and that's how I get the optimized version. So like we have this interpreter versus compiler duality. And we need both, because you can run things in full interpreter mode, and then like, what is the import time? We will see later. It's interpreted. Blue code is interpreted. At runtime is interpreted. And in compiler mode, the first 2 items are still run by interpreter, but what is left after Redshifting is compiled and fast, which is what you care about most of the time. The problem is that if in a language like Python, like everything is red. That's where we started from. Like, as a compiler, I don't know anything. I give up. Goodbye. So what we do is like tweak the semantics here and there, hoping not to remove too many Pythonicity, but having something which is less red and more blue. So the first tweak, and it's probably the most important, is that I codify something which in practice already happens. So in Python, at import time, everything can happen. You can do a lot of magic. You have decorator metaclasses. You can do monkey patching. You can generate code, everything. Like in Spy, the idea is that you start from entry point. You resolve all the module of the imports statically, including where they come from, including imports which are kind of inside of a function scope. So all the imports happens ahead of time. This is a big difference compared to Python, but it's not so different than what happens in normal program anyway. And at this point in time, we have basically all power of a fully dynamic language. You can do all the metaprogramming that you want, and a lot of this good stuff that happens in Python libraries happens at this level. Imagine SQL alchemy, you are taking a definition of the class and you are generating a lot of accessors and logic to make it an ORM. This happens, and it should be doable, it will be doable in SPI. Or something like Fast API. It takes annotations and adds all your function to a list of URLs, and this is something which happens at import time, so you, like a pattern like that, it's also doable in SPI. But then, I declare that you freeze the word, and then all the stuff that you could do before, that they become immutable. So, like if you try to modify a class after the freezing point, you get an error. Usually you don't do anyway. And that's the semantics of the language. And then you execute. And in the middle, optionally, you can do redshift. But it's actually like redshifting is kind of just an optimization phase, but the semantic of the language is the same before and after. So let's try and dive deeper inside. So this is like, if you don't look at the blue decorator, like this is pretty standard Python code. Like I have a closure, and I have a function which creates a closure and generates a function to add 5, another to add 7, and I can call it. What if I redshift? Then we can see that what happens is that after redshifting, I really create 2 different copies of the function. One which is add 5, which has this constant built-in, and this other which is add 7, which is constant built-in. So like all the cost of creating a closure and calling a closure is gone. But we can do better, because here in the first example, I passed a constant, but I can pass a type. So that's one way of doing generics. So I decided I want to have a function to add integers, and then I call makeAdder passing ints, and one make other passing strings, and then I have 2 addition functions specialized for my types. This is generics ugly. And you see that I created, again, 2 versions of the function. This becomes interesting because like this is like integer addition, which is fast, and this knows that to do string addition, you need to call an helper function. And again, cost of dispatch is done at redshifting and not at runtime. This is not a nice way of writing generics, so I have like some kind of syntax sugar. I have this decorator, which is blue, the generic. I don't like this name, I might change it. But basically, this means that instead of calling this function using round parentheses, you call it using square brackets. So like, this is basically calling this blue add function, passing str as the type, and then I have an implementation function which uses this as annotation. Like, it's very dynamic if you think about it, more dynamic than you can do with MyPy or Python type checkers, because they will not be able to understand this logic. In SPI, it just works because the type checker happens later, after this has been executed. So if I do this, I can see that basically that's what we would expect. So like the first calls add of str, and which is this function, and the second called the integer version of it. And of course, I'm not limited to function. That's how I can do types and generic types and containers. And that's how I do arrays, for example. The other tweak that we need to make to the Python semantics is that types needs to be enforced. In Python, type annotation are completely optional and are completely ignored by the interpreter. They're just hints, but the interpreter doesn't care about it. In SPI, you do. So in a case like that, here you're trying to call inc function with a wrong type. If you hit this code path, you get a type error. And note that you get a type error here at this point, not here. Because like, the type error is when you try to call the function and the type annotation is wrong. But in this case, you don't get an error, because as in Python, if you don't hit this line, it's not a problem. So I can, if I use the interpreter, this just works. But I basically have two ways of dealing with errors during the shifting. One is lazy errors, which is what I showed now. So if I do, then this call, which was inc of some string, is redshifted into array statement. And this is like, it's something which is useful, for example, if you are doing some refactoring and you don't want to fix all your code at one time. But actually the default is to have eager type errors. So if I don't do anything, then like if the interpreter works, but at the rest shifting I get a type error and it tells me that yes, I cannot call inc here because I got a string and I expect an int and the function, I mean like all normal error messages that you would expect from a compiler. And then the final is operator dispatch, because what happens in Python? In Python, when you have, for example, x plus y, it's equivalent to doing operator.add of x and y, which is like, it's actually more complicated, but let's keep it simple. You check the dynamic type at runtime of x, and then you call $add on it, passing the two types. So that's what happens in Python, and everything happens at runtime. In Spy, it happens something similar, but using the static types. So the semantics is different. So like what in Python you get a lot of genericity by just like executing stuff at runtime. In Spy you need to actually use generics to do that. But what happens is that the operator dispatch is done in two steps. So I get the static type of x and y, and then I call operator.uppercase add, which returns another function, which is the actual logic. And the function, which is the implementation, is called with the operands. But the idea is that these three lines are blue, so they are completely gone after the shifting, and so what's left is something which is very, very fast. But we still have the power of Python because I can still override and have custom types with overridden operators. And I can totally override the uppercase version of add, get item, or get add, and do like stuff based on the static type information that I have. That's one way, for example, of implementing function overloading without paying the cost at runtime. And finally, we have this two levels problem. And what I have so far is like the low-level core. So I have a module which is called unsafe, which allows you to deal with like low-level memory. And with this, you can, for example, declare a struct, and you can declare pointers. And with that, I can take like a pointer to array, to this struct, and construct a higher level type, which is, like for example, the super simple implementation of array. And you can see that the dunder new, like the important part here is this type lift decorator, which basically it's kind of a cast, but only from the static type checker, the point of view of the static type checker. Because the low-level layout of this object is what is in this special dunder LL field. So at runtime, this will be a pointer to array data. And it's the equivalent of when you are in C, you have like your low-level struct, and then you wrap in a PyObject star, and that's the equivalent, but without leaving the language. And this is, this is more or less the code which I wrote in the demo before. The demo before actually was a two-dimensional array, but this is kind of same concept. And then this is not something which I implemented yet, but just to give you an idea of where you can go. Once you have this uppercase, lowercase distinction, you can do stuff like, okay, I have a dunder get item of an array, and what is the index? I have this special oparg, which basically represents static information. You pass things like the static type of the operand, where it was defined. If it's a blue, you know also the value. And you can say something, okay, if I'm doing a get item of a single integer, then I use the specialized implementation just for single integer. Then if I do a get item of a slice, then I can do another specialized implementation for slice. And by composing this, then you remove all the abstraction of array, and what's left is just the actual computation that you're interested in. And of course, if I call get item on something which is not an int and not a slice, I write type error, and when I write type error inside the blue, then it's, well, it happens what I showed here, and you can get a compile time error or a lazy error depending on what you choose. So that's basically what I said so far. We have the low-level core. The standard library is in progress. I don't have it yet, but it's actually the next thing which I'm going to do. So now I have enough functionality and can start implement built-in types. Contributions are welcome, because that's actually a good point if you are interested in joining the effort, because you don't need to be a compiler expert to do that. You just need to know enough low-level stuff to be able to implement a vector or a dictionary. And that's it. Before finishing, I would like to thank Anaconda, which is my employer, because I'm fully paid for doing this. And I'm 100% on SPY nowadays, so like very good opportunity. You can find me on various social media, and if you are interested in this stuff, I suggest to follow my blog, because every now and then I write updates on it. So that's it.
Thank you very much. No question from Slido, but, oh, okay. So just entered. So you can go. Okay? Okay. It's Tortellini. Oh, wow. I have no question here. So would you mind getting for it? Thank you very much.
I have 3 questions. I will take not just one. Is type annotation Pythonic, in your opinion? Why we have to force type annotation when we can do type inference and at least reduce the usage of the type annotation?
So, type inference inside a function, I think it's totally Pythonic, because as a human you can follow it. Across functions like whole program type inference, in practice, it's very hard to do correctly. Like my experience is with PyPy. In PyPy, we implemented the interpreter in this restricted subset, which is RPython. And in RPython, we did whole program type inference. And it was a mess, because you have your program which works, and then you modify something in one file, and then you get complete strange errors, because it tells you that this operation is no longer valid, because like the type inference engine is not able to deal with it. Generally speaking, like type inference, it's good when it works, but it's very hard to get good errors, I would say. So I think it's better to keep it simple.
Okay, thanks. I don't want to monopolize.
In addition, is that all the blue code doesn't require type annotation, actually, because it's executed ahead of time anyway. So if you have a problem, you get a real type error. So like it actually makes like when I'm using MyPy, I always find hard to deal with these metaprogramming type annotations, because if you have a like classic decorator, which is logger, and it takes a function and logs its argument, what is the type? Well, we don't know, because it generally depends on the type of the. In Spy, this works out of the box, because it takes a function and you can like inspect the annotation and add the annotation of the new function without the type checker to know, because the type checker will see the concrete function object that you produced. So from this point of view, it's a big improvement over current situation, I think.
Okay, so I got the question from Slido now.
Okay.
We have a couple of questions about the comparison with Mojo.
Mm-hmm.
So, for example, given the growing interest in high-performance Python alternatives, what are your thoughts on Mojo as a superset of Python? Do you see it gain a real traction in the industry, or do you think it's more a niche tool for now?
So, disclaimer first, the people of Mojo are super smart, smarter than me. I'm sure they are in good faith and they try their best. That said, when they say that it's a superset of Python, it's not true. Because superset of Python means that if you take write random Python code and expect it to compile, and as far as I know, that's not true, and it's very, very hard to have something which is fully compatible with all the corner cases of Python. So if you are not able to run Django, or NumPy, or PyTest, then you're not a superset of Python. And so Mojo is a variant of Python, which makes different choices than Spy. We kind of play on the same field, but I wouldn't call it a superset.
Okay, thank you very much. No more questions. Thank you again, and thank you, everybody.